In this module, we want to help you understand the basic building blocks of radios that transform electrical currents into electromagnetic waves and back. To set the stage, let's consider again our wireless device and how it connects to the network, either a cellular network or a Wi-Fi network. In another module, we talk about the antenna in this device and the electromagnetic wave that propagates between the mobile device and the network device. For this discussion, we want to talk about three different wireless devices: a cellular phone, an amateur radio, and an AM transmitter kit. The cellular phone is a digital radio built out of integrated chips. The amateur radio uses analog transmission and is made of a combination of chips and discrete components. The AM transmitter kit is also an analog transmitter and is made up largely of discrete components. These radios look very different, and indeed they're used for different applications, but they have much more in common than you might think. Inside the devices on either end of a wireless link are special components called radios. Radios include common building blocks like antennas, amplifiers, modulators, oscillators, and filters. To illustrate in this AM transmitter kit, the information signal comes in through this connector and is amplified by an audio amplifier. It's then modulated using this oscillator circuit and an amplifier. It's filtered with a matching circuit and then sent out of the antenna. So let's look inside the cell phone. When we take it apart, there's a lot of user interface components. The radio functionality is implemented as several chips. So at a high level, we want to summarize the functionality of the building blocks shown in the diagram here. We will focus on transmission from one radio, called the transmitter, to another radio, called the receiver. When a device has both transmitter and receiver functionality, we often call the radio a transceiver. The simplest radio transmitter and receiver setup that I can imagine is a rudimentary version of the one we use for the EM wave module. The transmitter consists of an oscillator circuit connected to a power source, for example a battery, and an antenna. The oscillator uses the power source to generate an alternating current that is smoothly varying between current flowing in one direction to it flowing in the other direction. If we were to plot a graph of this current as a function of time, it would be a sinusoid with a particular frequency, that is, a number of cycles per second. This frequency is often called the carrier frequency in communications jargon. The oscillating current in the antenna induces an alternating electric field of essentially the same frequency around it, which then propagates according to Maxwell's equations. The receiver of our simplest radio setup is another antenna connected to a light bulb. The oscillating electric field around the receiver antenna induces an alternating current. If the intensity of the received current is high enough, this current heats up the resistance in the light bulb and creates light that we can observe. Because the oscillations occur much more rapidly than our eyes can resolve, the light from the bulb appears relatively constant. Now, how can we use this simplest radio setup for communication? If we turn the power source on and off at the transmitter with a switch, we see the light go on and off in the receiver. We can define a sequence of time intervals and turn the transmitter on or off in each interval, thereby conveying one binary digit or bit of information per interval. This is perhaps the simplest form of digital modulation and is called on-off keying, or OOK. How can we improve this simple radio? There are several ways. First, in the transmitter we can amplify the oscillator output and tune the parameters of the oscillator and antenna to create a stronger EM signal. An amplifier is an electrical circuit that uses the power source to boost the strength of its input current to produce a larger output current. Matching the parameters between the oscillator and antenna can get as complicated as we want, but we can obtain some pretty robust improvements with some simple rules of thumb. For the example of a dipole antenna, we can adjust the lengths of the two pieces of conducting metal. A good choice for many applications is to make the length of each piece equal to 1/4 the wavelength corresponding to the frequency of the oscillator and the EM radiation. Second, we can improve this simple setup by adding a filter and an amplifier in the receiver. A filter is a circuit that maintains the strength of some frequencies and suppresses the strength of other frequencies. For this application, we want a bandpass filter that passes the oscillator and EM radiation frequency and suppresses or rejects other sources of noise and interference. The amplifier in the receiver boosts the current resulting from weak EM radiation. Taken together, these improvements to the simplest radio setup allow the transmitter and receiver to operate over longer distances. Before we wrap up this module, I want to elaborate on the topic of modulation, which embeds an information signal into a carrier signal. Many circuit implementations can be modeled mathematically as a filtered information signal affecting either the amplitude or the frequency of a carrier signal. The former is called amplitude modulation, or AM, and the latter is called frequency modulation, or FM. As you might imagine, these modulation techniques are the bases for AM and FM radio broadcasting, respectively. But at least one of them is a basic ingredient in all modern wireless radios. To illustrate a few more aspects of this AM transmitter kit, we've powered it up and given it an audio source. This amateur radio receiver is tuned to a frequency of 600 kilohertz. When we play the audio and turn on the transmitter, we don't hear any of the audio in the receiver. We need to tune the transmitter frequency in order for that signal to be picked up by the receiver. This ability to tune the transmit frequencies allow us to have multiple radios operating on different frequencies without generating interference. A radio is a part of a wireless device that embeds information into electrical currents and in turn electromagnetic waves. A modern smartphone like this one contains a number of radios to connect to different networks and services. Radio design is an art form, but each radio contains some basic building blocks such as modulators, filters, amplifiers, and antennas.